When you look at the space shuttle, you're looking at a true icon of human achievement. It seems so perfect, like it sprang from a single brilliant idea that was flawlessly executed from start to finish. But the real story of how it was designed, oh, it's so much messier and way more interesting. And it reveals a surprising truth about how breakthroughs actually happen. I mean, think about it. This was the fundamental challenge staring NASA down in the late 1960s. They'd just been to the moon, and now they wanted the next giant leap, a reusable spacecraft. The problem? Nobody had ever built one. There was no blueprint, no instruction manual. They had to invent the process as they went along. We all tend to imagine innovation looking like the arrow on the left, a nice, clean, straight line always moving up. But the design of the space shuttle? Its journey was much more like this tangled thing on the right, a messy, winding path that honestly often looked like it was going completely backward. The big question is, why? To say this project was ambitious is, well, a massive understatement. The engineers themselves knew what a mountain they were trying to climb. They were trying to balance dozens and dozens of competing needs for a machine that had never even been properly imagined, let alone built. And here's the really wild part. This entire tangled journey, all the back and forth, it happened in an incredibly intense 2-year sprint. Just 2 years. From the first abstract ideas to the final design concept, it was all crammed between 1969 and 1971. So to understand how they pulled this off, we're going to act like detectives. We're going to follow the evidence trail of just one single absolutely critical goal: how much weight the shuttle could actually carry into orbit. Okay, so their target was a 50,000-pound payload. Now, to put that into perspective, the Apollo command module, that could only carry about 4,500 pounds. This wasn't just a little bit more ambitious. This was a monumental leap. So let's look at the design history, our first piece of evidence. In June of 1969, with design number 3, boom, they did it. They designed a shuttle that could carry 50,000 pounds. You think, okay, case closed, right? They hit their target super early. But that is not what happened. In fact, things get really weird. Just 2 months later, they produced 2 new designs that completely failed to meet the goal. The payloads dropped to less than half the target. So why? Why would you succeed only to immediately go backward? And the plot just thickens. In that same month, August 1969, design number 6 hits the 50,000-pound target again. It's this absolutely bizarre back and forth. Success, failure, success. This whole pattern just feels illogical. It looks like a team that's confused, maybe making a bunch of mistakes, just stumbling around in the dark. But what if it wasn't a mistake at all? This brings us to the first huge clue in solving our puzzle. This back and forth movement wasn't a mistake. It was a deliberate strategy, and it's called oscillation. Oscillation is pretty much what it sounds like, a strategic swing of the pendulum. You hit a target, then you purposefully swing away from it, only to swing back later. It's an intentional retreat. But why on earth would you do that? Because stepping back allowed them to learn. By reducing the payload, they could see how that one single change affected everything else, from the engine thrust to the fuel type to the shape of the wings. Oscillation wasn't about failing. It was a really powerful tool for understanding how every single part of this complex system was connected. So that explains the back and forth, but there's still another piece to the puzzle. The second clue is a concept called the accumulation method. Now, this chart illustrates the point brilliantly. If progress were linear, this chart would only ever go up, right? But look here. In November of '69, design number 9 met 3 of the 6 key goals. Okay, good. But the very next design, number 10, only met 1. Then design 11 met 2. Again, this just feels like a step backward. By the numbers, they were getting less successful. So how can a design that meets fewer goals possibly represent progress? The answer is accumulation. It's a non-monotonic process, which is really just a fancy way of saying it doesn't always move in one direction. See, the goal wasn't to maximize the number of check marks in any single design. The true goal was to accumulate knowledge by exploring different combinations of successfully met goals, even if the total number went down for a little while. So now we've got our 2 clues, oscillation and accumulation. Let's put them together and see how they solve the case of how the space shuttle was really designed. And this is the payoff. Look at this chart. You see how goals for the payload bay and capacity are met in Design 9? Then they disappear completely in Design 16, only to pop right back up in the final design? That's oscillation. And notice how different combinations of goals are met in each version, with the total number of checkmarks staying flat or even decreasing before, bam, they finally achieve all 6 goals at once. That's accumulation. It was a path of learning, not a straight line to the finish. So we can distill this entire complex process into a simple but really powerful framework. First, you oscillate on individual goals to learn how everything is connected. Second, you accumulate knowledge from all these different combinations, even if it looks like a step back. And finally, you combine all those deep learnings to achieve the final breakthrough results. Look, this is a fascinating piece of history, but what does it really mean for us today? Why does this 50-year-old story about engineering still matter so much? Because this isn't just about spaceships, it is a blueprint for any major breakthrough. It teaches us that true innovation is messy, that sometimes the most important step you can take is a step backward to learn something new, and that understanding how all the little pieces of a complex problem fit together is the most crucial skill of all, whether you're designing a rocket, developing artificial intelligence, or tackling climate change. Ultimately, what NASA's journey shows us is that breakthrough innovation isn't a race to the finish line. It's more like a strategic dance, a deliberate movement between pushing forward to hit a target and then pulling back to understand the whole system. And that leaves us with a final thought. What seemingly impossible problems could we solve today if we just embraced this method? If we had the courage to value learning over just linear progress and weren't afraid to take that strategic step back in order to achieve a truly giant leap forward?